of the IPS which is online. So just to prove this, I wrote a very small and stupid program which is called HTTP IPS detect, which purpose is mainly just to listen to the packets sent back on the network. So you send the SYN, we'll get a SYNAC. We're going to listen to the SYNAC and all these kind of packets. And then just analyze and provide a good view of, well, some TCP fields which are interesting, or IP fields, like TTL, IP ID, Windows sites, etc., etc. And we'll see that with just 2 URLs, there are many, many ways to detect different kind of IPSs and behavior. So a very basic standard URL, just getting the home page, and then very old exploit, you know, this code red stuff. So quite stupid. And let's see some results. First of all, I'm going to, well, just detect a layer 7 firewall, you know, what we call these layer 7 application IPSs, or whatever, which usually work as a reverse proxy. So here I just launch the baseline, I get the home page, and I see that the IP ID mechanism, okay, IP ID is generated first is 0, and then you've got numbers which are incremented. So this is typically a behavior from Linux. And then I see that the server, the banner, is Microsoft. Okay, this is a little bit stupid example. You're going to tell me I can change the banner, etc., etc. Okay, just to show you that we get some kind of interesting information. Maybe a little bit more interesting, SYN flood protection. Let's say somebody here is working with, well, some SYN cookies. So I send the SYN, I receive a SYNAC, and I see that the TTL started at 64. Then I keep on launching my request, and I get the answer. And the answer now is a packet which has been generated with a TTL, original TTL of 128. So we see that the system that sent me back the SYNAC with probably a SYN cookie, I guess, and the system that answered and served the web page are not the same. So I've got somewhere an IPS on the way. With the TTL, I can calculate the distance, see if it's on the same network than the web server, or maybe 1 or 2 hops before, and get ready for maybe some kind of insertion. More advanced again, pending sessions. You know this kind of attack where you just connect to a port like port 80, okay, SYN, SYNAC, ACK, and then you just try to keep alive the session without sending any command. So at the end of the day, if you do that maybe 10,000 times, server is not going to accept any more connections. So, well, basic protection is just, you know, to behave, for an IPS to behave a little bit like proxy, you know, just getting SYN, SYNAC, ACK, and just waiting for the first command, HTTP command. So if he doesn't get the command, it doesn't transfer the session to the server. And this is what happens here. Okay, I received the SYNAC with TTL started at 256. I received the ACK of my first command, maybe my get slash, with once again this TTL, and then the rest of the session is done with a system which TTL started at 64. So once again, it's another system, and we detected this IPS. And well, maybe easier anyway, it's just when you send an attack and you get a reset. You see at the reset, just have something like, okay, it's different TTL here, and completely different IP ID. So, okay, for sure, there's a system on the line. So, you see here this very basic example to show that IPSs, whatever you do, we saw layer 7 firewalls, we saw reverse proxies, we saw SYN cookies, session pending protection, all this, and each time there was a way to detect it. So it was different products. Some of them I don't even know, I just tested on the internet, but it's very easy to detect, okay? So big picture here, problem is the environment. Because how can you hide your IPS? It must behave exactly like the remote system. So, okay, if you just protect maybe like one web server, you can try to copy and, well, to patch whatever just to get exactly the same TTL, exactly the same kind of sequence number, IP ID generation, all this, that's okay. But I was talking about something I call real world. In the real world, you don't buy an IPS to protect one web server. You want to protect your infrastructure. Maybe 50, 100 servers, thousands of workstations. So you're going to tell me that for each and every IP address, you're going to tune your IPS just to say, well, I'm going to make sure that we've got exactly the good TTL, the good IP ID, and it looks exactly like the server. No, it's not possible. So we saw this for some TCP and IP fields, but we've got some problems also with MAC addresses. When you're performing some NAT and you're working on a local network, we see that the same IP address is going, well, different IP addresses are going to answer with the same MAC address. Then you detected the NAT, very easy. Stack internals also. Why? Because systems do behave differently when handling, well, fragments, when handling all this kind of stuff. Okay, so there are different sizes of tables, and this is the kind of difference you're playing with when you're doing some insertion attacks, exactly the same. You will see that this stack is going to start dropping frags after maybe 30 seconds. And then the IPS is going to just drop it after 3 or 4 seconds. It's usually for performance reasons. Here, once again, you've been able to block it, or to detect it, sorry. And that's true also at application layer. Okay, just think about all those HTTP request smuggling, response splitting, and all this. Okay, each time it's because you can bypass IPSs, you can corrupt cache, you can compromise some sessions in some cases, just because the proxy or the IPS or the web server don't behave exactly the same. Well, it's like, you know, recently there's been a way to bypass some filters that were not really able to detect a URL, which is still valid for the server, but not for the IDS. Once again, it's the same. So in terms of solution there, well, there's no solution. That's what I said. It's not possible to maintain this kind of infrastructure. One server, well, let's say you've got a few servers and you're going to patch them. Maybe something is going to change into the stack. And then you have, once again, to go over your IPS and change all the tuning. It's not possible, differently. So maybe the only solution is to run exactly the same system, but then it will be vulnerable to the same attacks. Perfectly useless. Okay, let's talk a little bit about signatures now. Because, well, okay, detecting IPSs is okay, but not so cool. With signatures, there are many things we can do. But first, we have to understand different kind of signatures we will find into IPSs. First, we've got what we call generic signatures. They are here with kind of global pattern to detect, well, generic threats, okay, like shellcodes, buffer overflows, all this, okay? We've got, I include into this category, very basic kind of behavioral signatures, which is like, you know, if I see 10 authentication attempts in less than 1 second from one source to one destination, I say it's a brute force attack. I get it into this category. Then we've got the vulnerability or vector-based attack signatures. So they are going, these kind of signatures are supposed to be more accurate because they are going exactly to sign the vulnerability and the way it's been exploited. So should be quite resistant to any kind of obfuscation, very accurate, but we'll see it's still not perfect. And then you've got the exploit-based. You've got the very exploit, and you want with your IPS to block this exploit. Not no any variant, just this exploit. That's even more accurate, but of course that's too accurate. And just keep in mind those very important issues, false positive, performances, and maybe evasion. I say maybe because, once again, what's really important for you, if you don't want to get fired, is first to ensure that your network should have good performances and doesn't drop packets. Talking about some generic signatures. We've got very basic and standard patterns, like, you know, just NOP sleds, null sleds, all this, usual shellcodes. We saw this kind of very limited behavioral, which is just dumb statistics. And here, the problem is false positives. If you're too generic, you're going to generate a lot of false positives. And then you're not going to activate this signature. So, stupid example is just, if you've got 20 times when you just count null and you see that you've got more than 20 nulls in a row, you're going to say, oh, okay, that's, I think, a kind of shellcode for buffer overflow, I don't know. No. In a lot of binaries, you will find this kind of sequence of packets. So that will be a false positive. Then you have to be a little bit smarter and just say, okay, so let's also sign the short jump, which you will find usually after this knob sled or node sled. And then you've got a good signature. So you see the problem with IPSs, is that signatures are far harder to write if you want them to be efficient, if you want them to run into production. And that's the reason why, out of thousands of signatures, only a few hundred are usually activated, then limiting dramatically the real security that provides this kind of device. Also, you've got this security policy and all the customization issues. Okay, let's say that an IDS can shout and say, hey, I see an SNMP packet with this public community. It's not good. If an IPS is doing that and it blocks this packet, you're going to get into trouble. Because usually, that's management. Okay, management is not secure. Your IPS is not here to define your security policy, just here to enforce it. So you see that a lot of signatures, a lot of insecure behavior are not going to be blocked by IPSs. And it's normal, or, well, anyway, that's the way it should behave. With this kind of generic signatures, evasion is usually very easy, because these generic signatures, as we saw, are, well, generic, but they've been worked on a lot, like this short jump after the node sled. So it's pretty easy just to evade this kind of signature with a little bit of changes somewhere. And also, there are always these performance issues that make signatures are going to be as short as possible, and then not going to be so accurate. Vector-based signatures. Here, the purpose of the game is just to sign a vulnerability, sorry. So it's completely independent from the payload, and it needs something far more advanced engines just, to detect it. Because not just detecting a few knob sleds or all this, it's usually far more, well, advanced. I say, let's see this signature, against this DCRPC DCOM exploit that I get from Snort. First of all, to ensure I don't have any kind of fault positive, you're going to try to analyze and make sure you've got DCRPC traffic. Okay, that's, well, pretty dumb stuff, test, but okay. And then what we're going to do is that we know that this vulnerability is the name of a NetBIOS resource, which is too long. So what I'm going to do first is try to find where is it NetBIOS resource. So you see, at this point, here. Whoops. Here, you see, it's the two backslashes, Unicode encoded, that are just, well, we're looking for them. And then, from there, we know that the size of the field is coded just before. So we go back, like 8 bytes back, minus 8, and then we compare the 4 bytes and make sure their value is larger than 256. If it's the case, we've got the exploit. So you see that signing vulnerabilities is very accurate. It needs a lot of work. It's supposed